2026, China is set to complete an astonishing number of mega projects in a single year, a scale of achievement that surpasses what many countries accomplish over several decades. These projects include the fastest passenger train on Earth, a dam taller than a 100-story skyscraper, entirely new cities, and nationwide energy systems built to support future demand. When compared with the slow progress of rail, airports, and power infrastructure in the United States, Europe, or even parts of the Middle East, China's pace of execution stands in a category of its own. Over the past 15 years, China has built at a scale never seen before in human history massive transportation networks, national power grids, industrial hubs, and entire new urban regions have emerged in a remarkably short time. The year 2026 marks a major milestone, as many of these long-term plans reach completion simultaneously. Every year, China adds more solar power capacity than the total installed capacity of most countries. Its new railway projects relocate and connect populations equivalent to entire nations. Its energy infrastructure is not designed for next year or the next election cycle, but for the next several decades. So how does China build so much, so fast? And which mega projects are scheduled to be completed in 2026? Let us begin with CR450, the fastest passenger train ever built. China already operates the largest high-speed rail network in the world, exceeding 45,000 kilometers by 2025 and carrying billions of passengers every year. In 2026, China will introduce the CR450, the fastest commercial passenger train on the planet, redefining the limits of ground transportation. During testing, the CR450 reached speeds of approximately 280 miles per hour. By comparison, most European high-speed trains operate between 185 and 200 miles per hour. Japan's Shinkansen remains below 200 miles per hour. Even China's current high-speed trains are capped at about 217 miles per hour. The CR450 pushes beyond all of them. Achieving higher speeds safely required dozens of controlled, incremental improvements rather than a single radical breakthrough. Engineers redesigned the train nose to reduce air resistance by more than 20%. Structural weight was reduced by roughly 10 to 15% through the use of carbon fiber composites and lightweight alloys. These changes alone improved energy efficiency by nearly 20%. Vibration control, braking systems, and overall ride stability were also upgraded. Noise levels were reduced to below 65 decibels at maximum speed, quieter than many city streets. At speeds above 250 miles per hour, air pressure becomes a structural challenge, not just a comfort issue. The CR450 addresses this with reinforced cabins and advanced pressure management systems. The result is a train that accelerates rapidly, runs smoothly, and remains stable at speeds once reserved only for experimental systems. But speed alone is not the real story. The CR450 is designed for China's busiest long-distance corridors, such as routes connecting Shanghai to major inland cities and Beijing to the country's economic heartlands. On journeys exceeding 900 miles, the difference between 217 and 280 miles per hour translates into hours saved. Overnight trips become same-day journeys. Business travel patterns change. Labor markets expand. Office locations shift. Entire economic geographies are reshaped by time savings alone. This project is part of China's broader industrial strategy, including Made in China 2025 and the China Standardized Electric Multiple Unit Program, both aimed at building independent domestic innovation rather than relying on foreign technology. Between 2021 and 2025, the Chinese government is estimated to have invested roughly $14 billion in high-speed rail research and development alone. By 2030, plans call for the production of approximately 500 CR450 train sets, and this is only one project among many that will reach completion in 2026. Even though high-speed rail is extremely expensive, with costs reaching tens of billions of US dollars per corridor, and some routes struggling with profitability in sparsely populated regions, China continues to push forward aggressively. For Beijing, high-speed rail is not just about ticket revenue. It is a strategic replacement for domestic air travel, a way to reduce fuel imports, cut carbon emissions, and integrate remote regions into a single national economic system. When trains begin to compete directly with airplanes in terms of speed and convenience, they reduce the need for airport expansion and strengthen urban connectivity without adding new runways. The CR450 is not just a train, it is a strategic infrastructure project. While high-speed rail is reshaping how people move on land, aviation remains essential for ultra-long-distance travel, international trade, and coastal megacities. And that brings us to the next major project scheduled to come online in 2026. In that year, Xiang'an International Airport, built to serve the city of Xiamen, will officially begin operations. This is a completely new airport, constructed primarily on reclaimed land offshore, with a total investment of roughly $7 billion. In its initial phase, Xiang'an is designed to handle 45 million passengers and approximately 826,000 tons of cargo per year, placing it in the same league as airports like JFK or Heathrow. The airport was built offshore because Xiamen's existing Gaoqi airport has been completely surrounded by urban development, leaving little room for expansion without major disruption. Rather than attempting piecemeal upgrades, China chose to start from scratch. Engineers constructed massive seawalls, stabilized the seabed, and created an artificial island large enough to support multiple runways and a full terminal complex. This approach is similar to Hong Kong International Airport, but built to newer engineering standards with far higher levels of automation. Inside the terminal, efficiency is the core design principle. Passenger flow relies on biometric identity verification. Baggage handling is managed by fully automated robotic sorting systems. Ground operations are coordinated through AI-driven traffic scheduling to minimize delays. The airport features 4 parallel Code 4F runways, each ranging from roughly 12,500 to nearly 15,000 feet in length, capable of handling aircraft such as the Airbus A380 and the Boeing 747. At peak capacity, Xiang'an can support up to 100 flights per hour. Long-term expansion plans project capacity rising to 80 million passengers by the year 2040. This reflects China's planning philosophy of building infrastructure not for immediate demand, but for the next half-century. The significance of Xiang'an goes far beyond convenience. Xiamen sits directly across the Taiwan Strait and plays a key role in cross-strait trade, manufacturing exports, and regional logistics. A high-capacity international airport strengthens this position and supports China's broader coastal economic strategy, particularly within the Belt and Road framework. In much of the Western world, new major airports are extremely rare. Most projects focus on expanding existing facilities and often face intense public opposition, legal delays, and cost overruns. As seen in cases like Berlin-Brandenburg Airport, China takes a different approach. When long-term forecasts indicate sustained pressure, China builds capacity far ahead of demand and then grows into it. This strategy carries financial risk if traffic growth slows. But Chinese planners are betting on long horizons, designing airports like Xiang'an to serve for 50 years or more. And this pattern will repeat again and again across China's mega projects scheduled for completion in 2026. Transportation is only one part of the story. In 2026, China is also completing some of the largest energy mega projects ever built. The most striking example is the Shuangjiangkou Hydropower Station in Sichuan Province. Once completed, it will become the tallest dam ever constructed on Earth. Standing roughly 1,033 feet high, that is taller than a 100-story skyscraper, higher than the Hoover Dam in the United States, which stands about 725 feet, and even taller than China's own Jinping 1 Dam at roughly 1,000 feet. This is not a prestige project. It is a strategic response to geography, energy demand, and risk management. Southwestern China relies heavily on hydropower, especially Sichuan, to supply electricity to major industrial centers in eastern China. Recent droughts expose serious vulnerabilities in this system, triggering power shortages and causing economic losses measured in billions of US dollars, most notably during the summer of 2022. Shuangjiangkou is designed specifically to reduce that risk. Its massive reservoir holds approximately 110 billion cubic feet of water, allowing excess water to be stored during the rainy season and released during dry periods. This stabilizes power output throughout the year. When fully operational, the dam will generate roughly 2,000 megawatts of electricity, with annual production around 8.5 billion kilowatt hours. That is enough to power more than 4 million households. Building a dam of this height in a seismically active region required advanced engineering. Instead of a traditional concrete gravity dam, engineers selected a concrete-faced rock-filled dam design. This structure can absorb seismic stress more effectively, allowing controlled flexing rather than catastrophic cracking under extreme pressure. The dam is embedded with real-time monitoring systems using internet-connected sensors that track vibration, deformation, and internal stress. These systems are critical in a region with potential seismic activity equivalent to major earthquakes. Construction pushed engineering limits, involving massive rock excavation, complex river diversion tunnels, and material placement with near millimeter-level precision. Strict temperature control was also required to maintain long-term structural integrity. In Europe and North America, projects of this scale face severe obstacles, including environmental opposition, relocation costs, and limited suitable sites. China takes a different approach. It prioritizes long-term energy security and still has untapped river systems in mountainous regions. For Beijing, energy stability outweighs short-term resistance. During construction, the project created employment for roughly 20,000 workers. Once operational, it will reduce carbon emissions by an estimated 7 million metric tons of carbon dioxide per year. But hydropower is only part of the picture. In 2026, China will also activate Linglong 1, the world's first land-based small modular nuclear reactor to enter commercial operation. It is located on Hainan Island. Linglong 1 has a capacity of approximately 125 megawatts. That is far smaller than traditional nuclear plants, which often exceed 1,000 megawatts. But its smaller size is exactly the point. Conventional nuclear plants typically take 8 to 12 years to build and often face cost overruns and delays, leading to project cancellations in the United States and Europe. Linglong 1 uses a modular design, meaning key components are manufactured in factories and assembled on site. This reduces construction complexity and shortens timelines. From groundbreaking in 2021 to grid connection in 2026, the total construction period is about 5 years, less than half the time required for large-scale reactors. Total investment is estimated at roughly $420 million. Linglong 1 represents a fundamentally different approach to nuclear energy. It is designed for flexibility, scalability, and deployment in regions where large nuclear plants are impractical. It also supports China's long-term strategy of combining renewable energy with stable nuclear baseload power to ensure grid reliability. Together, projects like Shuangjiangkou and Linglong 1 show that China's energy strategy is not focused on a single solution. It is building a diversified system designed to withstand climate volatility, economic shocks, and long-term demand growth. And in 2026, many of these plans move from blueprint to reality. China is focusing on smaller nuclear reactors because energy demand does not always match massive power plants. Remote regions, islands, industrial parks, and smaller cities all need reliable baseload electricity, but they often lack the scale or political support required for large nuclear facilities. Linglong 1 is designed to fill that gap. It can operate independently or in clusters, supplying electricity, industrial heat, or even desalinated water. With a capacity of roughly 125 megawatts, Linglong 1 can generate about 1 billion kilowatt-hours of electricity per year, enough to supply power to roughly 500,000 households. Safety is a central feature of this design. Small modular reactors rely on passive safety systems. They do not depend on external power sources or human intervention to shut down safely. If cooling systems fail, heat is released automatically through natural processes. This significantly reduces meltdown risk and simplifies emergency planning. While small modular reactor designs have attracted global attention for years, no country has successfully brought a land-based unit into full commercial operation. The United States has approved designs but has not completed construction. The United Kingdom is targeting the 1930s. Russia operates floating reactors rather than land-based ones. China is moving first. If Linglong 1 performs as expected, China will gain a standardized nuclear product that can be replicated domestically and exported internationally. Many countries cannot afford large nuclear plants or lack political consensus to build them. Smaller standardized reactors offer a more practical alternative. Linglong 1 addresses a core challenge in China's energy transition, adding reliable low-carbon power without waiting a decade or betting everything on massive single-site facilities. This flexibility is becoming increasingly important as China reshapes its national energy structure. While nuclear power provides stability and hydropower offers storage and flexibility, solar and wind energy in China are expanding faster than anything else. By 2026, China's energy system will reach a threshold no other country has achieved. Renewable energy capacity will match or even surpass coal, becoming the backbone of electricity generation. This shift is not driven by rooftop panels or scattered turbines. It comes from massive centralized projects. Across the Tibetan Plateau and northern deserts, China is completing solar and wind bases on a scale comparable to entire national power grids. Some individual solar facilities cover more than 230 square miles, larger than the entire solar industry of many countries. These are fully integrated systems. Solar fields feed directly into substations. Wind farms balance output when sunlight fades. Grid-scale battery storage smooths fluctuations. Ultra-high voltage transmission lines move electricity thousands of miles from western deserts to eastern cities. This transmission layer is critical. Most of China's population and industry are concentrated along the coast, while the best renewable resources are deep inland. Instead of building power plants near cities, China built the world's largest long-distance transmission network. Some of these ultra-high voltage lines operate at roughly 1,100,000 volts. Each line can carry power equivalent to several nuclear reactors combined, with transmission losses under 3% across vast distances. This approach solves a problem that slows renewable deployment in the United States and Europe, where clean energy projects are often delayed by grid bottlenecks and permitting conflicts. China plans generation and transmission together. The scale is difficult to grasp. In a single recent year, China added more than 200 gigawatts of solar capacity. That is more than the total installed capacity of most developed nations combined. Wind power expanded at a similar pace. China's long-term logic is straightforward. Build renewable capacity far beyond current demand. Electricity consumption is expected to surge as transportation becomes electric. Data centers expand, and industry shifts away from fossil fuels. Cheap electricity attracts factories. Stable electricity attracts data centers. Clean electricity reduces dependence on imported fuel. When combined with hydropower and nuclear energy, renewables become the core system rather than a supplement. Total investment across these energy mega projects is estimated to exceed $140 billion. Taken together, China's massive projects, from the fastest passenger train on Earth to dams taller than skyscrapers and energy systems stretching across continents, make 2026 a defining milestone. Most of these projects were approved and funded many years ago. 2026 is simply the moment when long timelines converge. While infrastructure in much of the world slows under regulatory complexity, political division, or fragmented decision-making, China accepts higher upfront risk to lock in long-term capacity. It trades flexibility for execution. Whether this proves to be overexpansion or long-term foresight depends on what comes next. But that is the real story behind China's largest mega projects coming online in 2026.